Welcome to a lecture on dynamic ecosystems for the Ecosystems of the Future course in Restoration of Natural Systems. My name is Richard Hebda. I'm an adjunct at the University of Victoria and curator emeritus at the Royal BC Museum and a longtime lecturer in the Restoration of Natural Systems program. In this presentation, we're going to be looking at how we understand what happens to ecosystems as they change based on what we've seen in terms of changes in the past, changes that we can see occurring in the present, and also projections, particularly in the context of climate change. And at the end, I'm going to provide you a couple of key restoration strategies. Can't be comprehensive in the way I look at this thing, but having some idea of where to go with all of this knowledge that you gain from this lecture is very helpful. I'm going to summarize the key messages at the start and repeat them at the end so that you see where this is all going to go. Widespread climate change is underway. This is a prime driver, not the only driver, but a prime driver of ecosystem change. Human activity on the landscape is another one. Ecosystem change is already underway, and that change is fairly rapid. Past climate changes, like those that are projected and have already occurred in the past few decades, will foster widespread ecosystem changes. So ecosystems are going to change now, absolutely. Natural ecosystem change takes place at the species level from within, through in-migration from other populations and local losses within the ecosystem. An ecosystem change lags climate change and may not be gradual. In other words, there may be sudden changes by the crossing of thresholds. Second set of key messages, the amplitude and the rate of change have few recent precedents. In other words, what we're going to see in the next decades and centuries have not really been seen for a very long time, thousands of years at least. Ecosystem instability is likely for many decades and centuries, and that's because forcing through changing climates will not stop for at least 1,000 years. General features of future ecosystems can be projected, but their composition and structure and trajectory of change is really difficult to foresee, and you'll see why that is as we go through the presentation. And the use of restoration, ranging from simple preservation of ecosystems to active manipulation, provides adaptation strategies to the changes of ecosystems into the future, but it can't stop widespread ecosystem transformation because they're being driven by climate change, and climate change already underway cannot be manipulated by humans. A great place to look at what kind of changes at various levels is presented here at this website. I strongly urge you to look at it, and you'll see a huge amount of very thoughtful and stimulating information. So let's start with climate change. Right now, climate change is underway. Annual surface air temperature trends are unambiguous. The temperatures have increased by a significant amount, and if you look at this plot, you'll see they've increased anywhere from 1 to 1.5 degrees Celsius, depending on where you are. This shows both sea surface temperatures, which have changed less, and land surface temperatures, which have changed more. And these changes are smoothed using something called the lowest mathematical function. We're reaching record temperatures in terms of what we have observed since humans have been recording such things. And if we simply look at May 2020, land and ocean temperatures as percentiles, in other words, how much do the temperatures vary in each of these little squares from what the average should be or has been, we'll see that in the month of May 2020, large parts of the globe recorded very high, in fact, record temperatures. Notable and very interesting are the changes in north-central Siberia, just incredible changes of 5 to 10 degrees Celsius compared to normal. There are very few places in May that were lower. May was either tied for or the warmest May ever recorded in human history. But you can see it's all red, and some of it is record red. So that's in terms of difference from the typical occurrence. And in terms of percentiles, if we take a look now at land and ocean temperature departures from May in 2020, this is compared to 1981 to 2010, which is already a time of warming. You'll see that in some parts of the world, again, notably in northern Siberia, temperatures have increased, were not have increased, but were as much as 5 degrees Celsius plus warmer than they normally would be. Now, if we took a look at another feature, which is the occurrence of extremes, this image shows extremes by decade relative to the 1951-1980 mean. And I apologize, I haven't got anything newer than 2013, but it illustrates the point clearly. The flag of France, one can imagine, looks pretty normal from 1951 to 1980. But as we look through the decades, whether that be in the land summer temperature at the top or the winter summer temperature, you'll see that the occurrence of temperature is shifting out of the normal constraint or pattern, which is in the dotted green, and the tail end, the extreme tail end, which in 5180 is 0.1% of extreme temperatures, by 2011-2013 is 14.1%. which is a huge increase, a massive increase in the occurrence of extreme temperature events. And that's both in the summer and in the winter, less so in the winter. And if we had the data for the complete decade, 2011 to 2020, we would see that that 14.1% number is much, much greater. And we have very much shifted the natural distribution of temperatures, and the flag of France has effectively disappeared off the image. We know why that is. These changes are occurring, both the average temperatures and the deviations from average, as well as the extremes. And that's because the amount of carbon dioxide and other greenhouse gases, expressed in parts per million, is increasing, rising, and it's rising very rapidly. It exceeded 418 parts per million in 2020 for the first time in, and this is important, 3 to 4 million years. In other words, we haven't had this amount of carbon dioxide in the atmosphere for millions of years, essentially from before the start of the Ice Age, called the Pleistocene. The pre-industrial values were only 280 parts per million, that's in the 1700s, and more than 30% of that rise has occurred in the last 15 years. The Earth's surface temperature in response to rising greenhouse gases has increased somewhere about 1.2 degrees Celsius or 2.2 degrees Fahrenheit. And just keep this in mind, because we've been very concerned, broadly speaking, experts have, of not exceeding 1.5. That's pretty much guaranteed now, or not for certain exceeding 2.0 degrees Celsius warmer, and that is almost impossible to prevent at this point as well. So, very different climate in the future, very different types of ecosystems. So just a summary of what's going on with climate change, because climate change is the major driver of ecosystem change, especially when combined with human disturbance. The change is widespread, occurring at a large amplitude, is occurring very rapidly. It's ongoing and persistent. We're not returning to absence of change. Variation is occurring, and extremes are occurring in climates and in weather. And these climate changes may cross critical climatic thresholds, leading to climate regime shifts rather than a gradual change, sudden changes, which then essentially recalibrates the atmospheric conditions to which ecosystems must respond. So now let's take a look at the present conditions in terms of what's going on ecologically. So ecological transformation is now underway, both in physical and biological systems. And the physical systems drive biological systems, and the biological systems, individually organisms and species are responding, but the ecosystems are responding to physical changes in the landscape as well. Daily temperatures are rising. The sea ice is melting, and glacial ice is melting. So these are physical changes. Storm intensity is rising. There are more intense storms, including hurricanes. The amount of fire activity, maybe not so much in the number of fires, but the size of the fires and what they consume is increasing. Flooding is increasing and is widespread. Lake levels and river flows are changing, both at low levels because of drought and high levels because of extreme rainfall and moisture events. The sea level is rising and the ocean is acidifying. So these are all physical, chemical changes that are going on. And in response, we're seeing tree decline and death. No doubt we're seeing that on the level of herbaceous and shrubby species. We're seeing insect and disease outbreaks, much more frequent and widespread than in the past. And we're looking at species range shifts. I should add to this that ecosystems are already changing as a consequence. Some examples of physical changes in British Columbia's mountains. The glaciers are shrinking and melting away, and this image shown in the Coast Range shows very rapid retreat of a mountain glacier and a bare landscape because it's yet to be colonized by plants, and this has happened in the last few decades. Another example of physical changes are droughts and floods. I'm using here an example of the low levels last year, 2019, of the Cowichan River, where water had to be pumped out of Lake Cowichan to have water run in the Cowichan River itself. On the other hand, we have examples in Europe in the past few years of tremendous flooding. So extreme events in response to changes of weather, which are being driven by climate changes. So we can see at the same time that there are biological consequences of these changing climates, biological impacts. The most obvious one, the one that everybody comments on, is the decline and, in fact, death of cedar on the east side of Vancouver Island and around Victoria. This decline is linked to a late summer drought, and the image I include here illustrates conditions in Colwood, British Columbia, on the Royal Roads campus about 2017-18. And many trees have died in the understory on that campus, or many have declined with only branches in the lower portion and the top portions dead. And if we look at other areas, cedar is also declining, the tops dying, as you can see by the reddish branchlets in the middle of the screen in the East Kootenays, and this is near Cranbrook, British Columbia, in about the year 2017. These kinds of changes, as I mentioned, are linked to summer drought. And I have a student at the Royal Roads University who is now going to look at the changes in the past 15, 20 years when a lot of this death has taken place. But early on in the 2000s, I looked at this situation when we were first beginning to see the decline and death of cedar. And the blue line shows you basically how much moisture deficit is there in the summer months. And if you can see that, not much changes. There's sort of a variation that goes on starting around 1955 to about the year 1998 or so, and then in the late 1990s and early 2000s, the summers become very dry. So moisture deficit is a consequence of how warm it is and how little precipitation there is. And my suspicion is, though we haven't got it here, that the moisture deficits between 2010 and 2020 have been very intense in that area where the blue line drops very far down. So it's a 5-year mean of cumulative deficit anomaly. It just basically says how dry was it in the summer. Summers are getting drier, cedars are dying. Other trees are beginning to suffer as well. Hemlocks, grand firs, and even now Douglas fir. We have examples of some of this death of other tree species on the Sunshine Coast. This is near Madeira Park, northwest of Vancouver Island, on very shallow soils over granitic bedrock right next to the ocean. And in this picture, what you see is not only dead western red cedars in the left, distant background, but dying and dead lodgepole pines because the soils, which are shallow and mainly moss debris in pockets on the bedrock, dried out during the summer. This shows the phenomenon in general. The next picture shows you, even though it's very wet on the ground, it's just had been raining, the pine trees on these very shallow, small pockets of soil have died, and you can see that very clearly, the dead trees in the middle of the image. Even though this is a pretty wet climate, broadly speaking, compared to Victoria, the trees nevertheless have succumbed because of drought. Other consequences, biological consequences, are responses of diseases and pests. In this particular case, the well-known pine beetle outbreak, which began in the early 2000s, expanded very, very widely, essentially consumed most of the pine trees, not only lodgepole pine, but they went after ponderosa pine trees and removed them in some places completely from the ponderosa pine zone in southern BC, and far north into central British Columbia, far further than people thought they would extend. And this is because of several factors, but one of them being warmer winters, therefore the survival of the insect, drier summers, therefore drought consequences or stress on the trees, and also the planting or maintenance of very widespread one species dominated stands of forest, that is lodgepole pine, allowing huge numbers of insects to develop and spread in clouds, literally, to wherever lodgepole pines grew. So here's a pest example of the changes that are occurring as a consequence in part of climate change. So if we that's what's happened already. Now let's take a look at past ecosystems and the climate changes and their relationship in the past. There's a tremendously strong link between ecosystem characteristics and climate. So if the climate changes, and it's changed quite a bit over tens and hundreds of thousands of years because of the Ice Age, these climatic changes have consequences, and we have very different ecosystems as a result of different climates. We know that from these work we do that small climatic changes lead to major shifts. We know that these climatic changes lead not only to changes in the ecosystem composition and distribution, but into the key processes that shape where the ecosystems are and how they look, and in their essential ecosystem characteristics. And I will be talking more about that later. Looking at the past shows species responses to climatic changes. Looking in the past demonstrates that these changes can be rapid in ecosystems and that thresholds are crossed where you get whole scale or a great deal of change from one particular kind of an ecosystem to a different ecosystem, and that following a disturbance resulting from climate change, but other factors such as widespread fires, for example, or volcanic ash distribution, the return to equilibrium or stability takes a long time, often centuries. So how do we look at past ecosystems and their changes? We do that by looking at the mud, lake sediments, or other kinds of materials, either from the bottom of lakes or wetlands, which we can either see through exposures by excavation. In this case, the bottom of the lake was drained, and we can see 12,000 years of history in the bank in front of the researchers. Or we can take cores in those lake bottoms and study them. And what do we look for? We look for fossils, and the characteristics of the ecosystems are revealed through the fossils preserved in the sediment. So in this case, for example, the block of lake sediment, peaty lake sediment, right above the jackknife shows lodgepole pine cones that are about 12,000 years ago. Now, these pine cones are from trees that dominated the landscape in an area that's now covered by Douglas fir forest. So it tells us under different conditions in the past, we had different ecosystems. We can also look at microscopic remains such as pollen grains, and this is the pollen grain of samphire greens or saltwort or sea asparagus, and it's an excellent indicator of intertidal vegetation and tells us the position of sea level. And we see that sea level has changed tremendously over thousands, tens of thousands of years. It's also in the interior of BC an indicator of salt dry plant communities rather than forest or marshy plant communities growing at the edge of a lake. So a good indicator of conditions, sea level, salinity, and also of climate. So we begin our story about 30,000 years ago when North America enters this particular portion of the Ice Age, of the Pleistocene, and there's a huge cooling, and the cooling leads to very obvious physical effects, the growth and spread of ice sheets, which clearly transform any ecosystems that were living where the ice sheets spread to. They're gone. So they're essentially resetting the clock or the surface. And that's a climatic consequence of physical change that leads to very obvious ecosystem changes. 20,000 years before the present, after this glacial activity, the climates remain cold and dry. And this is about the coldest and driest that we see them in our region on the coast and in the interior of British Columbia. At this time in BC, or large parts of British Columbia, what we have is low elevation tundra. There are no forests. In this particular site that we're looking at, there may not have been any glaciers. There may have, we don't know, during the cooling. But the point is, when it was cold and dry, the landscape is not covered by the ecosystems that we know today, in this case forests. Rather, it's covered by tundra. So different climate, different ecosystems, and different processes. The freezing and thawing processes, for example, creates all the broken up rock that you see on the landscape in the image. The big melting takes place around 14,000 years ago. Valley glaciers melt and recede. The huge continental glaciers across North America begin to disappear as a consequence of warming. Then you get melting, you get some water on the landscape, obviously a different physical condition, and then you get you still, though, I have to say, at this point have cool or cold climates for a short period of time. And at this time, British Columbia and other parts of North America experience these climates are still cold, even though it's beginning to melt, and the landscape is populated by megafauna, mammoths, which you see, muskox, giant sloths. All of those lived on the coast of British Columbia and some in the interior of British Columbia. Now, these are all extinct, and they become extinct, just very briefly, because of the rapid climate changes that happen with the warming and presumably because of human hunting. But these animals, like open, wide, tundra or shrub environments, those rapidly disappear with the warming after 14,000 years ago. So again, the climate changes, the ecosystems change, and we see extinction. So big changes associated with major climatic changes. About 12,000 years ago, talking now on the coast, there's rapid warming, and Douglas fir expands along the coast to occupy pretty much the range that it does today. It also begins to move into the southern interior of BC. So just to re-emphasize, the climate has changed quite a bit, say since 20,000 years ago when there was tundra, and there were also extinct megafauna, and now we're moving into things that are familiar to us, all in the same place because of the climate's changing. So ecosystems changing in response to climate change. Following the sudden warming of 12,000 years ago, it actually gets a little bit warmer, so that about 9,000 years ago, as you can see in this picture, southern Vancouver Island is warmer and drier than today, and meadows are widespread where forest occurs, all around Saanich Inlet, for example. At first there are meadows, and later the oaks arrive, we don't know how, and then we get Garry Oak woodlands or a savanna. And that is under a climate that is warmer and drier than today by about a degree to maybe as much as 2 degrees. We don't exactly know. About as much as we've warmed already, or certainly will warm within the next 20, 30 years. So sudden warming to a condition warmer than today gives us a clue as to what we might expect. So we might expect in the future that would be less forest and more meadows and savanna. During that warm, dry time, there were fire activity was much more active. There were more fires than today, much more charcoal burning large parts of the province. And if we take a look at a map of the ecosystems as they were at that time, we quickly look on the left-hand side, 1 to 2 degrees Celsius warmer, and you can see, if you look closely, what the different colors mean in terms of ecosystems. But just simply look at the yellow one. Yellow is grasslands, orange is dry interior forests. 9,000 years ago, and this is the way it was, this is not some projection, we actually know this from the fossil record, grasslands were much more widespread than they are today, and dry forests also very widespread. And if you take a look on Vancouver Island, coastal Douglas fir ecosystems occurred over a wide swath of Vancouver Island and on the coast of British Columbia, including the lower mainland. And that you can see by comparison to the right-hand side. It says 3,000 years ago, but that's essentially the modern condition. So right there you see with just a few degrees of difference that the ecosystem distribution, and in fact their character, which I'm not going into here, was very, very different at that time. So we can expect similar kinds of differences in the very near future. This fuzzy image, sorry for that, shows you how widespread Douglas fir ecosystems were when it was 1 to 2 degrees Celsius warmer. That's the brown. And then you can see on the east side of Vancouver Island and even in the lower mainland that there were grassland type ecosystems, in this case Camas meadows or Garry Oak type meadows, widespread halfway up the east side of Vancouver Island. So very different ecosystems under a slightly different, warmer climate than today. And this is a fact. This is not a projection. This is the way it was. On a finer scale, even the wetland ecosystems were different. So 7,000 years ago and earlier, the sort of the warmer, drier time, we didn't have bogs and wooded swamps like we do today. We had marshes in the basins that we see on southern Vancouver Island. But then, as the climate changed 4,000 or so years ago, it became more moderate and moister. We saw the development of bogs in places where the marshes occurred. So the terrestrial environment changed with this small temperature change, as did the aquatic environment on land. Our modern ecosystem distribution and our modern ecosystems as we know them did not arise till 4,000 or so years ago, especially the coastal western hemlock and in interior cedar hemlock zones, the decline in grasslands extent, huge rearrangements of ecosystems, forming the modern pattern starting around 4,000 years ago. It's a time when western red cedar spreads very widely throughout the region to occupy the sites and the regions or areas that it does today. So we can see, going back just a few lifetimes of our major forest trees, major changes in ecosystem distribution and composition with very small changes in climate. And this example of a piece of wood that lived, it was a Douglas fir, lived about 4,000 years ago, around Heel Lake, which was drained. We removed the wood as the muck was excavated from the bottom of the lake. Take a look in the middle, and you can see very wide tree rings, very obvious, and then they become suddenly thin. We know from the study of not only this tree, but many other trees that were recovered from that basin, that this change happens at about the time that there's a major ecosystem reorganization in British Columbia and many parts of the world. And the change takes place into this different climatic regime, which is the fine rings going off to the right, over a period of about 10 years. So this suggests to us that there can be major climate regime shifts, that the climate continues on for a while and may vary a little bit, and then suddenly something happens and the climate changes essentially permanently for this to under a new climatic regime or into a new climatic regime, as indicated by the rapid change of the ring width in this ancient Douglas fir. Let's now look at how we can see what the future might be based on projections into the future. And these projections, now I'm looking only on climatic projections into the future, not on human activity within those ecosystems, which create other complex issues to those changes. So let's take a look at what these projections say we might expect in the near future. Now, as we do this, we have to think about a few things before I jump into showing you what it might be like. We can project a range of future climates, but it's very hard to project what the ecosystems might be in response to those climates, because we really, it's complex to understand how a species is going to interact with a shifting climate and changes in other species associated with it. The current climatic change trajectory is for a high degree or amount of change. We're not looking at some small gradual blip. We're looking at a major change. Recall I said that we haven't had carbon dioxide levels like this for 3 to 4 million years. Since before the Ice Age, we're moving into a different world altogether. Continental and provincial projections point to a widespread geographic reorganization of ecosystems. In other words, it's going to be different. And we don't know exactly what that's going to be like, but we know where the climates of the future might be, so we can then perhaps project that under those future climates we might see ecosystems that are suitable for those climates. The changes will take place on a species by species basis. In other words, change does not take place as an ecosystem picking itself up and moving into the new climatic envelope suitable conditions. Some species will benefit, increase their range, others will decline. There may be variations in the responses over time, depending on which areas you're in. This is a complex situation, and also mediated by the underground fungi, the mycorrhizae. The projections that I'm going to show you are only a guide. An example is the climate of the hot, dry ecosystems of the Okanagan could occur, and it's projected to occur in the southern Northwest Territories by the end of the century. But how in the world you get this ponderosa pine and the species of the South Okanagan to the Northwest Territories in less than a century it's very difficult to imagine. So the trajectory of this change and the mechanisms by which the change will occur is unknown. And the projections and record of past changes, however, are consistent for different types of climate, and the projections and record of past changes are consistent with each other. In other words, we have a high confidence of the degree and the nature of ecosystem changes at some point when the climate and the changes, the migrations, etc., are in equilibrium. So in other words, we know these kinds of changes have taken place. We know the nature of the changes. So these projections do not scare us from the scientific perspective, but they are very major. We use something called climate envelopes. You essentially you look at the places where species grow, you define the range of where they grow by their climate, values such as mean annual temperature and precipitation, to define where those species, and in fact you can define ecosystems in a similar manner. And then you essentially look at where those conditions will be in the future. You map where the climate could occur in the future with climate change, with different models of climate change, with a small amount from those projections that don't suggest a lot of change to a very large amount to say there's going to be a great deal of climate change. We then compare the modern range and condition of the species or ecosystems to the future range. The loss of range, in other words, where species are likely to be lost or die in tree species, is much easier to understand than to imagine how they're going to expand and where they're going to end up. So let's continue looking at this. Here's an example of an important climatic value. January minimum temperature is basically how cold it is. And let's take a look at the difference between 2004 and 2080. If we take a look at that difference, on the left-hand side, the map shows you that there's a lot of blue and white, which basically means it's cold. If you can increase the size of your image on your screen, you'll see what temperatures in degrees Celsius that represents. If you took a look at the right-hand side, you'll see the cold is gone. We're into the green and browns and reds, or whatever that color, greater than 5 degrees Celsius temperatures as the January minimum temperature, which is the coldest temperature would get on a January day, which would usually in the morning. And you'll see there's essentially no frost anymore in the wintertime in January, the coldest month, on the coast of British Columbia, even as far north as the Queen Charlotte Islands or Haida. So massive changes in this very important climatic variable. And to this, you can expect very strong biological responses. Now, I am showing you essentially not the extreme, but the 90th percentile of change. In other words, the models that show a lot of climatic change versus those that don't show very much. I add that we are, from the best of what we can see in terms of what's happening now, on this trajectory that is expressed on the right-hand side. So big time change in a classic variable January minimum temperature. This kind of information has been used in a very important paper published in Ecology, references there, to show how ecosystem distribution might change into the future. By the 2080s, in fact. On the left-hand side, is the current distribution of ecosystems. They're using the colors that you would expect to find on the ecosystems of British Columbia, the Beck zone. If you look there, you'll see red is grasslands, yellow is dry interior forest, that would be ponderosa pine, interior Douglas fir. Green is coastal western hemlock. With their projections, you look at the right-hand side, and you see where yellow is, and you see there's a ton of orange, which is ponderosa pine climate in northeastern British Columbia, in the Peace Country, and in fact reaching up into the Northwest Territories. You can see the massive extent of grasslands, which is red. You can see huge increase in Douglas fir forest, which is the kind of orange in the bottom lower left of the image, and expansion of the lowland temperate rainforest, which is green, and disappearance nearly of all the high elevation, cool forest and the boreal forest. These are huge changes, and this projection is not for big time change in terms of climate, but sort of middle of the road change. The picture on the right is quite consistent with the kind of distribution of ecosystems from looking at the past. So here we see major ecological transformation changes from the climate of today, which is basically the year 2000 more or less, to 2080. So ecosystems of the future on this basis and on looking in the past are going to be very different in terms of their distribution And I can guarantee you that their composition and the processes and other essential ecosystem characteristics will also be very different. And we can look simply at western red cedar as a species model. So you just saw an ecosystem model of the future. Now let's take a look at the western red cedar. What might happen to it? The left-hand side, the modern distribution of the climate of western red cedar, which actually fits the distribution of western red cedar very well. Big time change, we look at the right-hand side, and we'll see that in the classic areas of western red cedar, like Haida Gwaii, Vancouver Island, the lower coast, the central coast, even as far north as the Alaska Panhandle, the climate is no longer suitable. That doesn't mean there won't be some cedars growing in damper sites, but you'll see essentially the lowlands have a summer that's too warm and dry for the cedar to persist. You'll note that the distribution has gone to the tops of the mountains, from the slopes of the mountains, disappeared from the valley bottoms in the interior cedar hemlock zone to the tops of the mountains. And then there's a whole bunch of increase in northern British Columbia. However, how is the cedar going to get there in this short period of time of now 6 decades, only 6 decades? So here's a model that shows you dramatic changes in the distribution of the climate and presumably of where the tree can grow of western red cedar. And this is quite consistent with the changes projected in ecosystem models. Here's another way of looking at it, which is essentially growing degree days. Now this is for growing crops, but I want use this to emphasize how the conditions are changing for species. So if you take a look at what can grow in British Columbia today, in the upper left of the image, wherever it's white, it's essentially alpine tundra. You can't grow very much. And down on the bottom are tropical crops, or tropical species in this case, not crops. Think of the natural species. Avocados and sugarcane with a lot of warm temperatures, long growing season, thousands of growing degree days. And you can look up what that means. So most of British Columbia is pretty cool. You can't grow a lot, mainly cereals, cabbage, potatoes, pasture. And just in the southern part of the province do we get into the standard agricultural crops we're familiar with. Now, you can look back and forth between this image and the next image, which shows you, again, high degree of change, but the trajectory that we're on now. The blue and white have disappeared. Grapes, plums, and peaches. The nice bright green color, that green occurred on the previous slide only in the southern Okanagan, a bit on the coast. Now you look at growing conditions as far north as Fort St. John. One can imagine a wonderful white wine called Chateau Fort St. Jean in the year 2085. That's how much of climatic change there will occur. And if you look down at Seattle at the bottom of the image around Victoria, you see orange. That means that in terms of agricultural crops, we could be growing avocados and sugarcane. So imagine those kinds of changes, in this case expressed as agricultural crops, expressed via native species. Big time change is coming to our ecosystems and species distributions. Another image here, it gives you an idea just on the left-hand side of the interior. Today, grasslands is orange. You can orient yourself, Penticton, Vernon, Kamloops. In the future, 2080, using the fossil record as a model, the grasslands very widespread. So huge changes in the interior as well as on the coast. If we take a picture view of this, here's a montane ecosystem above Kamloops in the middle elevation forests. You have a marsh growing at the edge of a beautiful lake surrounded by dense conifer forests. Using the fossil record and projections into the future, that lake would look something like this. The forests would be only up on the slopes, on the hilltops. The valley bottom would be all grasslands. You would see alkali deposited in salt marsh or alkali marsh conditions around the lake. So the marsh is gone. We've got alkali conditions, and the forest is gone, replaced by grasslands. That's a suggestion as projected from looking into the future and as indicated by the fossil record. Now let's take a look at the conditions into the future on a continental scale. And these very different models, different scientists doing a similar kind of thing. You look at today on the left, look at the prairies constrained to the southern half of our prairie provinces. And then you take a look at the ecosystems of the Western Canada and Western United States complex and different. If you now take a look at 2090, that's the model they were using. The prairies have expanded in terms of the climate, suitable climate, right to the border of the Northwest Territories. The tundra is much less extensive in the islands. You can see forest ecosystem climates on sort of Baffin Island and other parts of Canada where there are no forests today, where you have tundra instead. So these changes are occurring on a continental scale and on a global scale, and will occur on those scales. So just some sobering thoughts to put you into the context of what we're facing. During the Pliocene, 2 to 5 million years ago, we're now talking we already talked about how high our carbon dioxide is. Arctic temperatures were 19 degrees Celsius warmer than they are today at 390 parts per million. So give us some error of, say, even 10%, 30 parts per million. We're at 418 now, extreme in the summer, in the winter. Then we have a condition we're already at. Now, the Arctic areas warm much more rapidly because of differential latitudinal warming than do mid-latitudes and certainly the equators. The sea level was at 1 to 2 degrees Celsius warmer, was 5 to 7 meters higher. Not 1 meter higher, which many people are talking about, but 5 to 7 meters higher. This has to do with the Greenland ice sheet and how much it'll change. We've now warmed, we're guaranteed to warm more than 1.5 degrees Celsius. And unless there's some miracle, magical way of sucking CO2 out of the atmosphere, and the biological impacts lag or stay behind the CO2 concentrations and then the resulting climatic changes. So it's like pulling on an elastic. The elastic is being pulled. The global physical and biological conditions have to catch up to the CO2 levels we are at now. Keep that in mind as we go into the looking at restoration and what we can do. So, restoration and ecosystem change. A few thoughts. The degree and scope of change that we're facing is so great that we cannot stop it. We can reduce it by reducing CO2 emissions, and we can adapt. So we can reduce the amount of change, and we can adapt to the changes, but we cannot stop it. The way to approach this kind of a challenge is to look at resilience of ecosystems and key processes that keep ecosystems functioning, working together, species relationships, etc. Not putting them into risk by destroying them or causing major changes to them on the landscape. The strategies I will present are based on an understanding of past and projected ecosystem changes and on the importance of natural systems to us. So you will have learned about the importance of biological diversity and the elements of them, the importance of ecosystems to our psychological well-being, etc., etc. And restoration has a role both in reducing CO2 and other emissions, that's mitigation, but also in adapting to the changes that are inevitable. So looking at mitigation, which is part of restoration, what we want is healthy and functioning future ecosystems. In other words, we want nature to be able to move forward as the climate changes in the way that is done for long periods of time to maintain functioning, well, coherent, resilient ecosystems. First of all, healthy functioning ecosystems remove CO2 and keep carbon stored in them. That's very important because that guarantees us less CO2 in the atmosphere. So we need to by restoration or preservation and ecosystem degradation and conversion, because it's the second major source of CO2. And then, of course, with the loss of natural ecosystems, we lose services and options into the future. Plants remove atmospheric CO2 through photosynthesis. This is a guarantee mechanism, and the only one we have, other than reducing CO2 emissions. Degraded ecosystems release CO2 and endanger the removal processes. In other words, you don't have as many trees, the trees don't live as well, they're affected by pests, they die, they don't take the CO2 out. And degraded ecosystems intensify the risk of transformation, and they lead to the losses of options into the future. So you take out some keystone species or put in a bunch of roads, you degrade the ecosystem, increase the risk of transformation. So some obvious things. Preservation and conservation first. If you got it, keep it. It keeps the CO2 in the ground, in the soil, in the living biomass, and has multiple benefits. So the way we think about restoration, from preservation to intense activity, preserve, conserve first. The best way to let nature begin to deal with the changes that are going to happen. Optimally, on the coast, which is our ecosystems store about as much carbon as any ecosystems in the world, is about a 250-year-old Douglas fir forest stand. So any old growth has to be preserved. And anything that can be old growth soon, old forests that are 110, 20 years old, need to be preserved so they can keep the carbon in and keep taking the carbon in. The adaptation is also equal to restoration. So in other words, I've just talked about mitigation, how to keep CO2 where it is or reduce the amount of CO2 or take more of it out. Now let's take a look at the things that we can do to improve our adaptation to future conditions. So first of all, some thoughts. This kind of adaptation is best carried out at a landscape scale because climate operates at a landscape and oceanscape scale. It's a macro controlling factor from the North Pole to the equator. There's some really good landscape scale initiatives on conservation and adaptation. The Yellowstone to Yukon initiative is a good example. You can check that out. Y to Y. Maintain resilience. Ecological processes are key to keeping ecosystems together and working together. Like soil formation, for example, and hydrological processes. Resilience also helps maintain biological and cultural diversity, and connectivity is another feature of maintaining resilience. Minimize disturbance. Disturbance creates vulnerability, opportunities for exotic species invasions, risk to transformation, especially rapid shifting across thresholds, catastrophic transformations. There's an excellent example, the Garry Oak ecosystem restoration activities, well described in the book in which the Restoration of Natural Systems program was involved. It takes a holistic landscape level approach. It is an ecosystem with species that are likely to increase their range with climate change and they already are adapted to the kinds of conditions we might expect in the future. So preserve, conserve, and of course restore the ecosystem so that these species can expand their ranges, living together as part of an ecosystem that's adapted to the future. Understand essential ecosystem characteristics, focusing on key processes. I won't spend a lot of time on this, but it's the processes that shape the ecosystems and the trajectory and transformation. So here's a list of the kinds of processes characteristics that people look at. And if you read the paper in Harwell or consult the ER 311 notes where I kind of simplify this, you can see how this works and why it works and how one figures these things out. A really big question these days is assisted migration. Should we move nature or move species? People are very protective of their genetic material, say on an island or in the region. And why should we move something into the region? Because we're going to wreck what we already have and have inherited. And assisted migration is an important consideration. My answer is yes, you see it down at the bottom, but it takes some thought. It's region, site, and species consideration are involved in this kind of activity. There are resource and capacity limitations to move species. We simply can't move all the red cedar trees that would be moved into the future climate of northern British Columbia. And in any case, when would we move them? When would be the right time to do it? It's just very difficult to do on a very large scale. But have the discussion. If you're on an island somewhere and you're concerned about what the future is going to be like, have the discussion. Everybody openly talk about the ethical perspectives, the biological perspectives, the physical changes. But don't use some kind of concern or moral obligation you may think you have with nature to hold back your action. Decide the level of change you're comfortable with, and then we need to move on to be making some of these changes. Now, some of these changes are not such as moving alligators to Gabriola Island, but they may be moving some things on the mainland that are well adapted to drier conditions that might be on Gabriola Island onto the island, where they would naturally move in any case over a relatively short period of time. And I say yes to assisted migration, and I'm going to give you a couple of examples. The Garry Oak ecosystem and how to think about it into the future, and Oregon ash as a strategic species. So here, how might we think about where are good places to make an assisted migration intervention? For example, planting a Garry Oak in an area where it doesn't grow now. Here's a good indicator, sea blush. Think outside the box. Sea blush leads the way. Sea blush grows in sites that are a little bit more closed and damp than Garry Oak sites today. But they grow with Garry Oaks, and if those sites become warmer and drier and more open in the future, they are good potential sites to be planting Garry Oaks in. So look at where Garry Oaks, you know where most of us know where they grow, southern Vancouver Island, a little bit on the east. But look where sea blush grows. All those dots, the colors don't matter. They're modern sea blush sites, and you'll see that those, if you went to these sites, are openings on shallow soils, warmer sites throughout the region. So you can see the potential for moving Garry Oak certainly already into many sites up the east side and even central Vancouver Island, and thinking about some sites on the coast. And if we look at the model of where Garry Oak might be growing with the future climate, all of those sites pretty much, there's a few odd ones there, but pretty much are suitable for Garry Oak. So here's a good way of looking into the future and not getting too far past what might happen, and start moving Garry Oaks, planting them in potential sites as pre-adaptation. Oregon ash. This is not a species that's widespread in BC, but it does occur, and it used to be more widespread. It occurs a little bit further south where it is more widespread in Oregon and Washington State. If we take a look at a map of where it grows in the forest, you'll see that it actually is relatively widespread climatically on Vancouver Island, including up the east side of Vancouver Island, and very interestingly in the Alberni Valley, where natural populations occur. So moving moving Oregon ash into any of this region as a forest tree, anticipating conditions like you can see are well represented in the south of Washington State, wouldn't be a big jump. It's a species we already have, and we're certainly moving it within an area that it does occur. And in the past, I can tell you, Oregon ash occurred widely on either side of Saanich Inlet and up the Cowichan Valley based on the fossil record. So here, assisted migration, let's plant them in anticipation of future conditions. Other things, very important, all restoration people know this, is to foster nature and healthy ecosystems. In any case, maintain native species, remove invasive species. Many of the native species probably occurred, and some we know occurred, like camas, for example, under a warmer and drier climate, so they have in their genetic background the ability to grow in the future climate that we can anticipate within a few decades. So 1 to 2 degrees Celsius we can anticipate, then we can look at the kinds of species that we might expect that would be suitable for that. And many of the species we have are. We already know that from the fossil record. So fostering nature gives you resilience and mitigation, resilience in preparing for the future, mitigation in maintaining ecosystems that are keeping CO2 in the ecosystem, in the soil, and taking it out of the atmosphere. So I just used Nootka rose, pre-adapted species, very widespread, very adaptable. We want to keep it where it is and plant it in disturbed sites that are suitable for it. So that's a very good example of a native species, but camas is another one in suitable sites. So I've talked about the future, using the past, what's already going on, and projections. Big time change. Ecosystems of the future are going to be very different than the ones that we see today. Very major changes are going to take place in a short period of time, and restoration has a central role, right from preservation to assisted migration, in allowing us to mitigate climate change and be adapted for climate change. So reviewing my key messages again: widespread climate change is underway, ecosystem change is already underway, past climate changes like those projected and that have already occurred in the past decades will foster widespread ecosystem changes. Natural ecosystem change takes place at the species level from within through in-migration and local losses. Ecosystem change lags climate change and may not be gradual. We may cross some thresholds with very rapid conversion of one kind of ecosystem to another, one that may be transient or not. Key messages 2, the amplitude and rate of change have few precedents. We're going back to millions of years ago in terms of climate. Nothing like this has been seen for millions of years. Ecosystem instability is likely for many decades and centuries and will be increased because of human activity on the landscape, whatever that may be: logging, agriculture, increased forest fire occurrence, building of human settlements, conversion. The general features of future ecosystems can be projected. In other words, we can look at what they might be like in an equilibrium conditions with future climates, but their composition and structure and the trajectory of change is difficult to foresee. And restoration, from preservation to active manipulation, provides both strategies for adaptation, but cannot stop widespread transformation. So our future ecosystems are going to be very different. We can do something about that, but we can't stop the fact that the ecological face of the world is changing. Thanks to a whole bunch of folks. Thanks to listening to what I have to say for you. And I hope this stimulates you to want to do more restoration and understand your ecosystems.